Quantum numbers describe the electron's location, trajectory, and energy within an atom. There are a total of 4 quantum numbers that you need to know. The first quantum number is known as the principal quantum number, which is n. The principal quantum number describes the energy level the electrons is located in, and therefore the size of the orbital. The principal quantum number is always a positive integer. Therefore, it's always either 1, 2, or 3, and so on. The second principal quantum number that you need to know is the orbital angular momentum quantum number, which is L. L describes the shape of the orbital. For example, there are 4, orbitals S, P, D, or F are designated corresponds to numbers 0, 1, 2, and 3. The number 0 corresponds to the S orbital, the number 1 corresponds to the P orbital, the number 2 corresponds to the D orbital, and number 3 corresponds to F orbital. The third quantum number is known as the magnetic quantum number, also known as ML. The magnetic quantum number, or ML, describes the energy levels in a subshell and the orientation of the orbital. So it ranges from -L to +L. One note that you should know is that if L, the orbital angular momentum quantum number, if L is equivalent to 0, then ML is always equivalent to 0 as well. The fourth quantum number and the final quantum number you need to know is the magnetic spin quantum number, also known as MS. MS is either always +½ or -½ +½ means that the electron is spinning upwards, -½ means the electron is spinning downwards. So with the orbital angular momentum quantum number, known as L, there are 0, 1, 2, 3, and so on. So if L is equal to 0, we can say that L equals 0 is the S orbital. And if L is equal to 1, then the electron is found within the P orbital. And with 2, the D orbital. And with 3, the F orbital. So it's a good time to mention that an orbital is a region in space where an electron is likely most to be found. So with a principal quantum number, it designates a specific principal shell within an atom. So if we say this is the nucleus of the atom, and this would be the first shell of the atom, this would be the second shell, and that would be the third shell. Here, we can say that the first shell is n equals 1, n corresponding to the principal quantum number. The second shell, n is equal to 2, and the third shell, n is equal to 3, and so on and so on. So the third quantum number, ML, so if ML is 0, this means that, like I said before, L is equal to 0. The reason for this is that in the S orbital, so if I write here, if L equals 0, ML must be 0. The reason for this is because there's only one S orbital per energy level. So with the p orbitals, which is L equals 2, there is a possibility of 3 magnetic quantum numbers. So there is a choice of px and py and pz orbitals. But with ML, it is equivalent to either -1, 0, or +1. The reason for this is because there are 3 p orbitals per energy level. So an electron can be found in any one of these. The specific electron that you're looking for can be found within any of these. So each of these p orbitals represent 1 energy level. And each of these corresponds to -1, 0, or +1. So all of this happens within the p orbital, and the p orbital is when L is equal to 1. So px, py, and pz can be in any order -1, 0, or +1. +1. It just literally depends on your preference, whether you want it to be py to be -1 or py to be +1, but as long as it is clarified in your answer. So now we can talk about d orbitals. So d orbitals correspond to the orbital angular momentum quantum number L equals 2. So if L is equal to 2, there are 4 possible energy levels that each of these d orbitals can accommodate. So for example, this energy level can accommodate that d orbital, and that one can correspond to that one can accommodate that one to that one, and that one to that one. So there are 5 d orbitals that we need to know: dxy, dxz, dy squared, dx squared, y squared, and dz squared. So if L is equal to 2 for d orbitals, we know that ML must have 5 possible numbers. So we know that we can have -2, -1, 0, +1, and +2 for d orbitals, because these 5 energy levels correspond to the 5 different types of d orbitals. So now we can move on to f orbitals. So with f orbitals, there are a total of 7 ML numbers that you can use to correspond to the electron. So with an f orbital, the orbital angular momentum quantum number, L, is equivalent to 3. So if L is 3, there are a total of 7 possible ML numbers. So ML can be -3, -2, -1, 0, +1, +2, +3. Remember, ML is the magnetic quantum number, which describes the energy levels in a subshell and the orientation of the orbital. So, f orbitals can have 7. Orientations. So 7 different energies that the electrons can be accommodated within. So over here, you can check out some images of an f orbital. It's very difficult to draw out, so this image will be a better representation if you guys want to have a look, which is just over here. And completely the same as a d orbital, it just literally corresponds to each of these ML numbers. So here we are going to go through an example. So an example in question that we're looking at is carbon. So we're going to pull apart this electron configuration that we're given for carbon. So this is just carbon neutral, just carbon as an element, and we're just gonna pull it apart and write down the quantum numbers for each of these, so you guys can get some clarification, some clarity about quantum numbers. So we can do 1s2 first. So with 1s2, we can write that n is equal to 1. Next quantum number, is L equals 0. The reason for this is because it's located in the s orbital, and s orbitals corresponds to L equals 0. So the next one is ML. And if you guys remember, I said that if L is 0, ML should always be 0. The next one is MS, and for MS we write plus or minus a half. The next part of the electron configuration is 2s2. So here we can write n is equal to 2 because it's in the second principal energy level. L is equal to 0 because it's in the s orbital. ML again is 0. MS is plus or minus a half. And the final one is 2p2. So here, 2p2, we can write n is equal to 2 because it's in the second principal energy level. L here is 1 because it corresponds to the p orbital. ML is equal to minus 1 or 0. And MS is equal to plus or minus a half. The reason why ML is equal to minus 1 or 0 is because it's located within the p orbitals. And according to Hund's rule, electrons choose to fill up the energy levels one by one first before doubling up. The reason for this is due to mutual electron repulsion. So that's the reason why ML is minus 1 or 0. And we can think back to these. So you'll be filling up like that first. So that is why ML is minus 1 or 0.